morning, everyone. Good afternoon. My name is Andrew Marsbon. I'm the technical manager of our additive department here at Saratech. We're going to be talking about Materialise Magics today and how to get the most out of it if you have a powder bed printer. Now, this session is going to assume that you have some familiarity already with Materialise Magics. So it's going to be a little bit more of an advanced strategies session. And the most benefit will be for customers that have a powder bed printer. However, a lot of these strategies are applicable to other print technologies as well. Here at Saratech, we use primarily HP Multi-Jet Fusion, which is a type of powder bed printer. We're printing with nylon PA12. However, a lot of the things we'll talk about are also applicable to things like SLS or a SAF technology. So with that, let's go ahead and get started. We are going to talk about three main topics today. We're going to be talking about the file preparation and fixing. Now, if you've used Magics before, you know it's a great, powerful tool for fixing files. We're not going to go too deep into fixing, but I'm going to cover one strategy that is kind of overlooked. So I'll talk about a more advanced file fixing process. We'll look at how we can reduce part weight and create strong parts for your powder bed printer. Typically, when we're talking about powder bed printing, the parts are printed solid, whereas with like an FFF technology or FDM technology, you'll have a honeycomb structure. So the topic we'll look at is how do we create those structures for powder bed printers. Then, of course, we'll talk about nesting strategies. Magics is really great for nesting large amounts of parts into a single build very quickly and efficiently. So we'll look at ways we can do that and things specific to the powder bed process. And then lastly, we'll talk about some interesting ways you can expand the use of your printer. A lot of times people think of their build envelope as the maximum size part that they can actually print, but with the tools in Magics, you can very easily split up parts, take large parts, make them into sections, and we'll talk about how we bond them together and get final parts, assembled parts at the end. So just one way to kind of expand your use with your printer. So with that, I'll jump right into Materialise. And let me go ahead and minimize this in the background here. I'll just leave this open in the background. So we'll go ahead and start. I already have my Multi-Jet Fusion HP printer loaded in here. So I'm going to create a new scene. And when you have your part scene here loaded, I will bring in the parts. So I do have a sample part for today. Now, the first thing we'll look at is our demo part. This part is a stepped file that an engineer created, and he said I needed this 3D printed. So at this point, I'm going to just assume that I don't have much more communication with that engineer. I'm just going to go ahead and do what I can on my end to get the part ready for printing. Now, as I bring it in here, Magics is going to highlight with yellow lines areas that need some fixing. And I can also see here that there is some extra artifacts that I don't want on this part. So for a little bit of background as to what this part is, this is actually a forming tool used by an aerospace company for forming sheet metal parts. And we have been working with this company for a while now and produced a lot of tooling for them. And it's a really great application with the HP Multi-Jet Fusion printer. Now, this part on here is the actual final part that is going to be made out of metal. And that was accidentally included in our exported model here. So we want to go ahead and get rid of that because that's not going to be printed. We just want the forming block underneath it. So when I bring a part into Magics, and if there's some cleanup I need to do or there's extra features or parts, the very first thing I'm going to do is I'm going to go into my edit in part scene. Now, we already have a build scene open here, and this is where all my parts I pack in are going to be. But when I when I hit an edit in build scene, it's going to open a new scene up, and it's just going to have this one part in here. So any changes I make to this part, they're going to get updated in the build scene over here. So I'm just going to be working here. Now, when I go into that edit in part scene mode, I have a lot more options and different ribbons here. So first thing I'm going to do is I'm going to open up the shell window. And this is going to show me how many shells make up your part. Ideally, one shell should be one part. But here we actually have a lot. We have 34 parts. So the question is, can I just simply select this excess and get rid of it? Well, let's see. If I highlight this here, okay, that's the block. but not the entire block. What about this next shell here? This is only a part of this shell here. So it looks like I wouldn't be able to just simply delete it just by marking a couple shells, because it's kind of all over the place. I'd have to selectively go and find which shells correspond. I mean, I could. It's not a crazy number of shells that I'm working with here. Well, let's just assume that this is too tedious and we can't do that. So um, what I'm going to do is I'm just going to go ahead and manually delete it here. So I'll go into my marking ribbon. I'm going to go ahead and click Mark Surface, so I get a larger selection. And then it does give you some options as to how you want to select that surface. I'm going to go ahead and use the brush tool so I can quickly swipe along the top here and select a lot at once. Okay, so I selected a part here that I don't want, so I'm just going to hold the Shift key, click again, and unselect it, as well as this right here. And then I want a little bit more taken off here. And I'm going to just work my way around the part. This won't take but a second. Then we have our edge here. Okay. So that's pretty much everything I want gone. So I'm just going to hit the delete key and see what happens. All right. Yeah, we got rid of most of it. You can see we have the backside of some triangles here from the part that we deleted out there. So we got to clean that up. At this point, the part looks pretty good. So I'm going to just attempt a regular auto fix. And for the most part, auto fix works like more than 90% of the time for me. I just click auto fix once and I'm good to go. So we'll see if autofix is here, because we did change the model up quite a bit. So maybe not. Let's see here. Okay. It looks like autofix did a lot more harm than good. It tried to fill in holes and restitch things that were not right. So that was kind of to be expected. I did kind of mess this model up quite a bit. I could go ahead and invert our normals and then select everything that's remaining. But I'm not going to do that. I'm going to do something that tends to be, at least I kind of forget that it's there, but it's very powerful, which is the shrink wrap part. Shrink wrap, basically, as the name implies, it's like you're putting a thin cover over everything. So any errors, holes, bad edges, that all gets covered up. So I'm going to go here. I want the entire part, so I am going to use the global shrink wrap. If you're dealing with a very large part and you don't want to shrink wrap everything, you could do local. When you're doing local, you'll have to mark those triangles or shells first, or surfaces first, and then you can do that. But we're going to globally do this because it's not a very complex part. Now with shrink wrap, you will lose some resolution, some fidelity to the part. That's to be expected, right? If you're putting a shrink wrap over something, just like in real life, if you put it over a textured surface, you might lose some of that texture. But the way we preserve that is just by reducing our sample interval here. Now, and so that's going to look at, a much finer section each time, so you're not losing as much detail. The trade-off to a smaller sample interval, though, is it's going to use more of your system memory. So right now I have a 0.2 interval. Let's say I bring it down to a 0.1. Now I'm going to use 1 gigabyte of memory. And if I make it even smaller, let's say I go 0.05, I want to capture every detail. Now we're using almost 3.5 gigabytes of RAM, and that's quite a lot. For the purpose of this demo, though, just so this doesn't take forever to process, I'm going to go with 0.2 millimeters. Gap fill, I might have some gaps here, so I'll leave about a 0.5 millimeter gap fill, and we're going to hit apply and see if this is able to clean up our part. And the more complex your part is, the longer this process will take. I've done this one before, so it should only take a couple seconds here. And sure enough, so it looks like we cleaned up all those triangles on the top there. And I don't see much of a loss in resolution. As a matter of fact, it looks pretty much how I would expect it to. You can kind of see here, if you zoom in really, really close, a little bit of loss in fidelity here, but that's not a problem. I mean, the when this thing is printed, that won't even be noticeable. I could, if I was really worried about that, I could go back and reduce my interval again and have it take a little bit longer, but I don't need to. I'm going to go back over here to the part fixing info and just make sure that everything looks good. Sure enough, we are good. We only have one shell for that one part. And so we're ready to print this. Now, let's go ahead and talk about printing this. So I am here in my build volume. You can see that this part does not fit in the build envelope. So, it's doesn't mean we can't do it. We actually have some pretty cool strategies that we're going to talk about right now for making parts fit in here. And that's going to be the lap joints. Going over here back into our part scene, I'm going to put a plane about halfway through it. And as you can see here, nothing is actually really aligned to the coordinate system. See how this is not actually aligned to X. If I look at it to the right, it's not quite aligned to our other axes. So I'm just going to go ahead and create a new plane. I can select any one of these. I'm just going to select this last one here and click perpendicular with indicated triangle. And then it's going to see here, it might be a little hard to see on the screen, but there's a blue triangle. Doesn't matter which one on this face I pick, they're all in the same plane. So I'll pick this one right here. And now I've created a new plane in the U direction, a new custom direction. I'll turn on that section and I'm going to go ahead and drag it until it is about halfway in the middle of the part. Doesn't need to be exact here. Okay, now we're going to go ahead and cut the part in two. Now, there are lots of ways you can cut parts in half. You can do a thing like a polyline where that gives you, full control to make whatever shape you want. I could do some crazy zigzag here with rounded edges. If I hit apply there, you'll see I get a new part that has this zigzag. But what I want to do here instead is to create a lap joint, tongue and groove joint. Now, if we go to the section, you can obviously do a basic cut, but if we go to the drop-down box, we have lap joint. Now, the lap joint has several different parameters you can set. There is an explanation of what each parameter is right here. Notch height A corresponds to how deep that tongue and groove basically lock into one another. Your offset is kind of the lip around the edge is your offset. That B value right here. And then you have a couple clearances, right? You have the back of the tongue and groove joint to the other face. You have the side, and then you have the part where they mate on the outer skin, basically, if that makes sense. If it doesn't make sense, don't worry. We'll go through it a little bit deeper and see. Now, what we typically like to do is the longest notch you can stand for, you should put, because that's going to increase your part strength. That's basically how deep one part is slotting into the next part there. So the more you have going in, then the stronger your part is. However, the longer you make it, now that means you have a tongue and groove that's sticking out much longer. So if the goal is to reduce your build space, now that you're eating up some of that space. I'll show you what that looks like here. So I'm going to hit apply, and I'll bring this here. And now you can see we have that tongue and groove joint. So now the part is much shorter. However, this distance here from here to here is now 20 millimeters. And if I extend that even further and further and further, then it's making this section longer and longer and longer. So ultimately, you're not getting the full advantage of this the longer you go. But it is a trade-off between strength and build size. So one other thing to note here is, what should I use for my clearances? Notch clearance, front clearance, back clearance. Well, that's going to depend on your printer specifically. Even if you do have an HP printer, there might be slight differences in your fusing power, and you might have a little bit higher or lower clearances. So the best way to go about it is just to create a test part. And what I like to do is I'll just go here in Magic. You can create a shape. Doesn't matter what you create, box, cylinder, doesn't really matter. I'm just going to make something, call it, I don't know, let's call it 200 millimeters long by an inch by an inch. And we got a new part. And then what I'll do is I'll take this part here, this new part that we created, and I will section it up And when I section it, I'm going to go here parallel to the x-axis, and I'll just do multiple sections on that part. I'm going to go ahead and cut it, and I'm going to try this clearance, 3.3, 0.2, 0.1. I'll hit apply. It's going to create two new parts. I'll select this one part here. I'm going to move my section over a little bit and cut or punch. And then maybe I'll try something else. Maybe I'll try 0.2 with a 0.1 with a 0.1. And then I'll hit apply, and I'll make multiple cuts like that along the part. So what I'm doing is I'm essentially creating a test piece that has different clearances, and I can print this in one of my other builds, and I can see physically how they all slot together if they make sense. And then you can also go in Magic, so you can label your part. So I could put, if I wanted to, some text and say this is part A, this is part B, this is part C, and that way you can kind of keep track of which clearance is what. And that would be how you figure out your clearances for this. So, this is kind of the full strategy that we go through is we look at our part, we figure out what kind of clearance it needs, we make our evaluation for the length of the tongue and groove joint, and then before we can go and finally print this part, though, we still have another issue. And the other issue we have is going to be packing density. So now we do have our part in two sections here. And with powder bed printers, they are a very thermally dependent process. So you got to make sure that you're not overloading the machine with too many parts at once. So if you can see here, I got these two parts. They both fit in the build volume nicely here. I'm going to take a side view. Oh, where's my other part? Where did it go? Oh, it's just one over the other here. So I'm going to put them side by side like that. And so I got my two parts here. Now you can see I'm actually at a 16% packing density. Now for HP, the recommended packing density is between 8 and 12%, 10% being the sweet spot. And we're at a 16%. So we want to reduce that down a little bit. And how can we reduce that packing density? Well, if we go back into our scene over here, in the structures tab, we can actually create a honeycomb structure. Well, first off, let's talk about the different ways we can reduce the part mass. We can very simply go in and just do a shell or a hollow on the part. So if I do a hollow out on the part with a 3mm wall thickness and hit OK, what's going to happen is if I take a section of it here, you can see that we've created, let's see here, you can see that we've created a cavity inside the part. And that's going to have the powder, unfused powder, trapped in there, because as this is printing, there's really nowhere for the powder to go. It's spreading powder layer by layer. And so that's all going to be trapped inside the part. So that may or may not be an issue if you think that this part is of risk of being broken and powder being released everywhere and making a mess, then maybe this strategy is not the best. So then maybe the next thing we can do instead of a hollow is a shell, and a shell is going to leave one of the faces open. So in order for the shell to work, I do have to select a face to leave open, and I'm going to do the same thing, leave a wall thickness. And now we can see here that it's going to remove that bottom face, create a 6mm shell around the part, and leave the rest for us. So now we have that. Now that's fine too. That looks pretty cool. And this is one solution. Now, with this part in particular, the customer is going to be stretching metal with this part. So it does need to be very strong and rigid. And it's over this top surface that the load is going to be applied to, right? So if there's nothing underneath it here, the part is at risk of collapsing in on itself. So this may not be the best strategy either. So that brings us to our next strategy, which is going to be the structures, honeycomb structure. Now, this honeycomb structure creates this infill structure, very similar to an FFF or FDM 3D printed part here. And we have a lot of parameters that we can control. What are the parameters? Well, if you want to see, you just hover over it, and it should, sorry, if you go over the eye here, it'll tell you what each of those parameters A, B, C, and D are. Real quick, we'll go through it. Wall thickness is what is on the outer edge, so I've left it at 6.35 millimeters, which is a quarter of an inch. The detail size, again, is just your resolution. So finer detail is going to take a little bit more time. And then hole diameter. That's how big these hexagon cells are going to be. So I put them at 1/2 inch right now, 12.7 millimeters. And then the infill thickness is how thick the walls of the hexagon cells are. So I'll leave that at 2 millimeters thick. Last thing we want to do is we want to say which direction these cells are aligned to. Since I'm putting my force on the very top here, I want them to be aligned in that direction. So I'm just going to hit indicate triangle, select one of these on the bottom here, and now I'll hit OK. Now this is going to create that structure internally. So we don't see anything here. There's no open surfaces now. But if I go back here to my section view, you can see we have a honeycomb structure on the inside there. Let me go look from the top down and show you. So you can see that there. Now, within each one of these cells, there still will be unfused powder in there if you're using a powder bed printer. And that is, again, the same as what we talked about before with hollowing out the part where you'll have unfused powder in there. We haven't found that to be too much of an issue, especially because we're using a 1/4 inch thick wall. A 1/4 inch thick nylon is pretty darn tough, and you're going to have to try really, really hard to break open the part and release the powder. So we don't see that as much of an issue. The unfused powder too is lighter than fused powder, so it does reduce your part weight. And these honeycomb structures, these walls here, are basically accepting the load from up top. So you're not at risk of this part collapsing in on itself. So this is a really great way to reduce the part weight without really noticing much from the exterior. And you do get very good strength from this method as well. So I'm going to go ahead and do this to both parts. So I've already done it to the one part. I'm going to apply it to the second part here. And now we'll see our packing density has dropped down to 8%. Which is beautiful. That's really nice where we want to be. Again, 8 to 12% is the sweet spot for HP. So that means I have up to 4% more. And look at that. I have all this room here, all this room here. So if I'm running this job, I have room to put other part files in here and make more use of my printer. Again, with these powder bed fusion printers, the biggest factor in your price is actually your build height. Of course, the more you pack in there, it does drive the price up, but that build height is the biggest factor. So, I can only get this build this tall, 340 millimeters pretty much, but there's room to put other things in there. So that works great to get a very efficient build there. So this is the strategy that we use. Now you have two parts. What are you going to do with that? Now you have to figure out how you're going to put these parts together. Now, the clearances we left are such that it works well with an epoxy. The product we use is this Scotchwell DP100. It's a 2-part epoxy. You do have to put it in a little gun with some mixing nozzles. But I really like this stuff for a couple reasons. First off, it does have about a 5-minute working time. So you are able to apply the glue, put the parts together, align it. Clamps are fantastic if you have some sort of woodworking clamps to hold your two sections together. This gives you a lot of working time. The other thing too with the DP100 is it is quite flexible even after it's fully cured. And the flexibility, it matches the flexibility of nylon more or less, so that you're not getting cracking at the bond lines. The other nice thing too about the powder bed printers is you might notice they have a little bit of a rough surface finish after they're printed, and that helps the epoxy really stick to the surface. So we've had a lot of success sectioning parts, bonding them together using this product. Another product that HP recommends for their parts is this hybrid 4070 product by Loctite. It is also a 2-part mix. I believe it's cyanoacrylate base, so it's going to be more similar to a super glue. We've had some success with this as well. I've personally noticed that it is a much more rigid bond. So I have on one occasion seen it crack at the bond line. I don't know if that was because I applied the product incorrectly or if that's just the nature of it, but this is a product that I've heard a lot of people are using as well. And we've had some success as well. So we've talked about how we can take our printer. In the case of an HP, we got a 15 by 11 by 15-inch build volume, and we've now made a part that's significantly larger. And one other consideration to keep in mind is that stack up tolerance will be an issue. So if, anytime you make a large part in a printer, you do have to look at what your tolerances will be. The larger the part, obviously, the larger your tolerances need to be to accommodate those. So if you are stacking up multiple parts that do have a certain amount of tolerance to them, you get tolerance stack up. So just keep that in mind. So this strategy works really well for larger parts that need not as high of tolerance. Maybe about 20 thou tolerance is probably good for this method. For parts that are, two sections, maybe up to 20, 24 inches long. If you go much larger than that, then you're going to have more and more tolerance. We've once done a full size aircraft seat. So, something that's about 3 or 4 feet tall. And we had about 50 thou tolerance error on there. Which is not bad at all. So we did have to, kind of go after the fact and clean up some of the bond lines and everything. But since it was an ergonomic prototype, something that, we didn't need millimeter accuracy, we just needed it to be representative of what the part would feel like, right? A chair for a pilot, then it was a perfect solution. The alternative to this method, the thing is the HP is such a quick printer. You can do a full build in just 12 hours. We were looking at doing this on a large format FDM printer, and that would have taken us about 4 days of print time. So, significant reduction in print time. It would have been just a single part had we done it on our large format FDM printer. That would be the advantage there, but the disadvantage is that it would take a considerable amount of time to print. So the whole point here is getting out prototypes faster and faster, and this was our solution for that. So the last thing we'll talk about is going to be nesting strategies. Now you're probably familiar already. I'm going to go ahead and create a new scene here. Now you're already familiar with Magix and how it's really great for nesting. So let's talk about a little bit more how you get the most out of that. I'm going to bring a sample part in here, a little part. And this one here is, I need a lot of these. Customer wants a lot of these. So how do I get the most possible? Well, the first question is, how many can I fit in a build? And there's a couple ways to go about this. I personally like to just do a little bit of quick math and come up with a number. So what I'll do is I'll break out my calculator, and I know my HP printer has a build volume of 380 millimeters by 284 millimeters by 380 millimeters. Oh, I think I hit the clear button on that. 380 by 284 by 380. So 41 million millimeters cubed is my build volume. And recall earlier I said that on our HP we strive for about a 10% packing density. So I'm going to multiply that by 0.1. So that means of my entire build volume, by 0.1. That means 4.1 million cubic millimeters is my usable volume. So what I'll do here is I'll look at the part volume of a single part here. We're at 37,000. So I'm going to take this divided by 37,000. And it says here I can fit 110-ish parts into a build. Okay, so that's how I would typically do it. Now, this part is fairly compact, but if you have very large parts that are very sparse, right, they take up a large bounding box, but they don't have a lot of volume in them, then this method won't work very accurately, but it does get you in the ballpark. It's a good starting point. Now, another way, too, is to actually let Magix figure it out for you, and I'll show you that right now. So, I calculated 110, but let's go ahead and put just a really large number. Let's put 200 in there. I don't know if it can do 200, but we'll see. So what we'll do is we'll open up our 3D nester, and I'm going to go here into the nesting settings, and I'm going to enable multi-platform placement optimized for platform height. And what this is going to do is it's going to fill up the build volume. I'm going to go here to the general settings, optimize until a nesting density of 10%, and I'm going to let it run. And we'll see when we do that, it actually creates two scenes. The first scene was fully nested at 10%, and the leftover parts were imported into a new scene and filled up to the very top at 8% here. So if we go back to this scene that's fully filled at 10%, and I look at the number of parts here, I can see I have a total of 110 parts, which is great because I calculated before 110 parts. That's how many parts would fit in the build. So we're good to go. Now, let's go ahead and undo this. And I want to nest this part. With HP, you typically want to avoid flat surfaces being parallel to the build plate. So with parts like this, I give them a little bit of an angle. Oh, I must have two in here. I did. I give them a little bit of an angle. Really, you want more than 20 degrees to avoid stair stepping. And the other thing too is see how this has a cupped shape. For HP printers, you want to have the cup always facing up. That's going to allow heat from the printing process to come out and not get trapped in there and lead to issues known as thermal bleed, where you have excess heat in your part. So we're going to leave this up like that. So this will be our print orientation here. And we're going to go ahead and duplicate that part 110 times. And now I'm going to go into the nester again. Leave a 5mm margin to the sides, a 5mm part interval, that's the space between parts. Optimize my density until 10% packing density. I'm going to turn off this multi-platform and the optimize because I don't need it anymore. And I'll let this run. Now, actually, one more thing. We're talking about advanced strategies, right? So we want to talk about how these parts get nested. There's many ways that Magics can put these all in your build. The one I generally default to is fix bottom plane and then rotation angle. This one you can maybe leave it at 90 degrees, or if you're really trying to pack parts in there, you can go all the way up to 15 degrees. Now, what that's going to do is it's going to keep the Z axis pointing straight up, and it's going to allow your part to rotate in the XY plane 90 degrees at a time. And we'll see what that looks like. Okay, looks like it left out a couple because I couldn't quite get to that. Looks like I just left out. Yeah, looks like I just left out a single part there. We can go ahead and redo that. I'll bump it up to 11% packing density. All right, now we can see we're all in there. So that left all the parts with the cups facing up, but now they are rotated in the XY plane a little bit. So that's great. And the reason we do that is because we set our orientation how we wanted it to be. And when we're doing that, we look at what's important to us. So as we stated from the beginning, right, it's important to us that we don't have a single face parallel to the build plate. The other thing too is we don't want to have stair stepping. So we do want to have a 20-degree angle between that parallel plate, that face and the build plate, right? So as long as we maintain those two things, we're good. We want to not have a lot of restriction on the part. We want it to be able to be as free as it can be so that it can pack as efficiently as it can be. So let's say, for example, I didn't want the part to do that. Let's say I didn't care which way was up or down, right? I can go here into the part settings and just say fix Z direction. So that's going to basically allow the part to have that 20-degree angle, rotate in any XY direction, but the Z axis could actually be flipped up or down like that. So if I run that, you'll see that some of these are actually now facing, like this part here is now facing downward. This one is facing upwards. And we don't want that for this part. So there's actually a lot of different ways we can nest. And if you go into the Materialise Magics manual, you just go over here to the Help tab and click Manual, you'll find this chart here with the different nesting options. And there's an explanation of each one and how they are bound to one another, or what their movement restrictions are. So, people are familiar with the nesting tool. However, it is quite a powerful tool. It has a lot more features than sometimes people realize. So that's what this demonstration is showing. A couple other interesting things about the nesting tool here. If we go to our nesting tool, I did deselect this before, but Optimize for slice volume. Um, this is really great because with powder bed printers, you want to have a uniform slice area at each layer. That's going to help shifts in the bed temperature and give you a more uniform print with better dimensional accuracy. So by turning that on, you can see it's kind of reshuffling these parts over and over again. And the results are actually visible here. If you go to the Analyze tab and you click on Check Slice Distribution, what this is going to do is it's going to basically take an X slice. So I'm going to turn on an X slice here, and it's going to look at each and every X slice. And you see the red area is the sliced area. And it's going to basically plot that out, the sliced area compared to the Z height. And you can see here, we have a very uniform sliced area across the entire build. If you don't have that on, you might see big spikes left and right, left and right. And what that is doing is you're introducing more heat, less heat, more heat, and you get a less uniform build, less dimensional accuracy. So turning on that slice volume optimization is really great for the HP printers. All right. Oh, fantastic. So today I hope this was useful for everyone. We had some interesting topics. We talked about file fixing and advanced ways to fix files and reduce their part weight and get them ready for printing using that honeycomb structure and the shrink wrap tool. We looked at the nesting strategies just now, how to orient your parts, lock their rotation for your best build results. And then we saw how to section those larger parts, use lap joints, and the bonding strategies that we use here at Saratech. So with that, I will open it up for questions.
Yes, we have one question so far, and that is it possible to nest parts with different settings? For example, I need some parts to be in a specific orientation, but other parts can rotate freely.
Yes, absolutely. Great question. So we can actually, so this build here was all the same part, right? Let's say we had 5 different parts and they all have different orientation needs, right? Let's just say this part here can be oriented whichever way, doesn't matter, up, down. But then I had some other parts that did need to be oriented a specific way. Well, if I go here into the nesting tool again, I can actually go here into the part settings and click here, specify per part. So this is the area where we would check how I want to restrict the movement. I can turn on specify per part, and then when I hit OK, it's actually going to load a list of all of the parts that I have. So let's say there's a specific part that I want to keep, and I don't even want it to rotate in the XY plane or the Z direction. I could simply turn that on to translate only. And that will make that part only translate. It won't be able to rotate in any direction. So I could do that. Every part could have a different value, and I could change the angle, degrees of freedom there, and whatever I wanted to. So absolutely, you can do it for different settings all within one packed build. So very good question. Thank you.
I believe that is it for questions.